Hi, I'm Frederick, the micro hobbyist. First off, thank you for your patience. This episode took a little longer than planned because life happened. Long story short, some serious family event came up. And yes, that always comes first. So, let's get back to business. Today, we're summoning good old 80s magic with PLDs, Programmable Logic Devices that turn my 6309 build from pile of chips into something that almost looks intentional. Quick reality check. This episode took a while because PLDs are one of those things that look simple, right up until they're absolutely not. I recorded a lot of footage while learning this. Most of it got deleted, not because it was bad, but because I was confidently wrong. In the end, I simplified things so you can follow along, without needing a whiteboard, a therapist, and a second cup of coffee. Coffee. I've always been comfortable with the combinatorial side of PLDs, ANDs, ORs, truth tables, but the registered side? That's where PLDs stop being glue logic and start acting like tiny digital brains with opinions. Strong ones. Over the past few months, I've been shaping these chips into exactly what the 6309 needs, sometimes successfully, sometimes not so much. Here's to hoping I've got everything right. A PLD is basically a blank logic chip you can program into a circuit. Within reason, the datasheet says programmable, not infinite cosmic power. Instead of wiring up a pile of 74 series chip, you write logic in CUPL, compile it, program the device, and suddenly you've got a custom hardware in a tiny little package. Think of it like a software-wired Swiss Army knife. Combinatorial logic for instant decisions, registered logic for clocked behavior. That's how you build counters, decoders, state machines, bus logic, clock selectors, the entire digital buffet, again, within reason. Back in the late 70s and early 80s, computers were built from mountains of 74 series logic. Actual mountains, entire Alps of NAND gates. Then came the PAL, or PAL, Programmable Array Logic. One-time programmable, no undo, no mercy. PALs were basically logic tattoos. Better get it right the first time. Then Lattice brought out GALs, which were reprogrammable and much friendlier. The ATF22V10 I'm using is a direct descendant. After that came CPLDs, multiple PLD blocks stitched together with predictable timing. That's the world of the ATF 1504, 1508, and the ATF 750 I'm using here also. And then there's FPGAs, massively flexible, massively powerful, and massively capable of turning your free time into a second full-time job. A single PLD can replace a shocking amount of discrete logic. Decoders, gates, multiplexers, small state machines, and it keeps the board cleaner. One chip, one program, and yes, one very efficient place where mistakes can hide. In this build, PLDs handle address decoding, I/O decoding, wait state requests, clock stretching, speed control, and eventually interrupt logic. What used to take 20 or 30 TTL chips now fits into a few programmable devices, and still I can reprogram them later. At a high level, a PLD has three main pieces. First, a programmable AND array. That's where inputs and their inverted versions get combined into conditions. Those feed OR gates, which form your logic equations. And finally, The result goes into a macrocell, which decides whether the signal goes straight out as a combinatorial logic or stored in a flip-flop as registered logic. So, in short, AND builds conditions or combines them, and the macrocell decides when the signal changes. That's the recipe that turns a CUPL file into real hardware. Yes, it really is that simple, and also, somehow, not. Memory regions, I/O windows, chip selects, all programmable. Change the map, recompile, no soldering iron, no regrets. Different peripherals need different timing at different speeds, so the system requests 0 to 3 wait states, and the wait state generator stretches the clock via MRDY pin accordingly. I also use wait states intentionally as a form of software-selectable speed control. Yes, I slow down the CPU on purpose. And third, a utility PLD for the nice-to-have stuff. Shadow ROM, read-write separation, and an RGB speed indicator LED. Was the RGB LED necessary? No. Is it useful? Sure. Does it make the machine look smarter than it really is? Absolutely. Fun fact learned the hard way: not all PLD outputs are created equal. Depending on the device, output macrocells and buried nodes don't get the same number of product terms. Yeesh. If you've never discovered that at 2 a.m., congratulations, you have a healthy lifestyle. CUPL, also known as Compiler for Universal Programmable Logic, is the language that tells the PLD what to become. It's Boolean logic in a readable form, simple, direct, and perfect for this kind of work. You define pins, and then write things like A and B, not C, select from this address range, look up this table, remember this bit. The compiler outputs a JED file, which is basically the fuse map for the device. Then you program it. If it works, it's because you told it to. If it misbehaves, you told it to do it too. Just accidentally. WinCUPL, the graphical editor, is vintage. Not the fun kind, more like Windows 98 screensaver crash and took your work with it vintage. Instead, use the command line compiler. It's faster, more reliable, and it doesn't randomly rage quit. Let's start with the memory map decode PLD. This one decides what part of the system you're talking to based on the address. We've got constant block, a fixed region that stays mapped regardless of MMU page attribution. Then IO request, a ZAD-inspired name for the memory mapped IO zone. And memory request, a general memory access zone meaning RAM or ROM. Since I had spare outputs, I also generated a few useful chip selects here. ROM disable, speed select, IRQ and FIRQ register selects for future interrupt logic. Next up, the IO decode PLD. This one generates chip selects for devices like the timer counter, compact flash card, a CIA serial chip, real-time clock, and power-on self-test display. It also outputs WS0 and WS1, the wait state bus. Depending on the device and the current speed, it provides 0 to 3 wait states accordingly. That feeds the wait state generator PLD, which asserts MRDY, stretching the clock in quarter cycle steps using a counter, meaning 4 quarter cycles per wait state. If a device ever needs more than 3 wait states, we can use external wait inputs to hold MRDY low until the device is ready. Fortunately, some chips actually support that, which is very polite of them. I originally thought I could get away with just 3 PLDs, but fate decided otherwise. A 4th PLD mostly handles shadow ROM, read-write separation, and adds an RGB speed indicator LED. And yes, the PLD code may evolve as we go. Right now, it's still more wires and hope than computer, but we're getting there. Alright folks, a quick pause before we dive back into the logic maze. This episode is brought to you by PCBWay, who turns your schematics and Gerbers into real hardware you can be proud of. Starting at just $5, can you really afford to wait? They cover standard PCBs, multi-layer, flex and rigid flex, plus CNC machining and 3D printing. And if hand soldering has started to feel like a personality trait, they also offer PCB assembly. For projects like this, where revisions happen and tolerances matter, it's really great working with a fab house that's consistent and straightforward from upload to delivery. So, if you're building a retro computer, a custom controller, or anything you want to exist in real world, check out PCBWay. Link in the description. Huge thanks to PCBWay for supporting the 6309 Unleashed project. Now back to the magic of PLDs. Alright, quick pit stop in PLD land. This build uses 4 PLDs and each one has a very distinct role. The memory decoder, the I/O decoder, the wait state generator, and one, let's call it a multi-purpose utility chip. Or, if we're being honest, it's the junk drawer of the PLDs. Together, these 4 chips replace a small pile of discrete logic, while keeping the wiring sane. Let's walk through them one at a time using the actual CUPL files you're seeing on the screen. We'll start with the memory map decoder. This PLD's job is simple but critical. It slices the entire 64 kilobyte address space into clean, well-defined regions so the rest of the system knows where it's talking. At the top of the file, we've got the usual header, name, device type, revision, etc. Nothing exciting, but incredibly useful 6 months from now when you're wondering what version actually worked. Input-wise, this PLD looks at the E-clock, so decoding only happens when the bus is valid, as the chip is about big picture memory regions, not individual registers. Next, we define symbolic address patterns, things like FXXX and FFFX. This is one of CUPL's nicest features. Instead of hard-coding bit patterns everywhere, we define reusable address shapes and build the map from those. Using those patterns, we carve the memory map into 3 main questions. Is this the constant memory block used by the MMU? Is this the I/O window for the input and output calls? Or is this general memory, meaning RAM or ROM? Each output is qualified with E, so nothing fires unless the address is valid. And since I had a few spare outputs, I also generated some global chip selects. Things like ROM disable, speed select, and placeholders for IRQ and FIRQ priority encoder registers for later use. Next up is the I/O decoder. Think of this one as the nightclub bouncer. It stands at the door, checks the address, checks the access type, and decides which device gets to step onto the bus. Inputs include I/O request, read-write, the lower address bits, A0 through A7, the CPU speed bits, and a clock for asserting output enables. We pack A7 down to A0 into a single field called ADDR, which lets us match clean address ranges instead of writing a wall of Boolean logic. Each device gets its own slice of the I/O page. The timer, counter, compact flash card, dual ACIA, real-time clock, and the post display. I'm trying to stay somewhat compatible with the Coco 3 I/O layout, emphasis on trying, but in the end, with Nitrous 9, it's not all that important. Well, theoretically. Here's where this PLD really earns its keep: wait state requests. Different devices have different access times, and those timings matter more as the CPU speed goes up. So we cross-reference the asserted device and the current speed mode via a lookup table. Every row of that table basically says if the CPU is talking to this device at this speed, request this many wait states. The result comes out as a 2-bit value on WS0 and WS1. Those lines are shared across the system, so we only drive them when needed. Otherwise, they're tri-stated and pulled low by resistors. Among so many quirks in CUPL, there's a small one with a weird workaround. A pseudo register called WS_EN, whose only job is to convince the fitter to allocate exactly one product term for the output enable. Yes, it's a hack, and yes, it's intentional, and yes, PLDs will absolutely make you do things like this. Now we get to the wait state generator, or the clock stretcher if you prefer. It's the timing cop of the system. This PLD runs on an ATF750C and supports 0 to 3 wait states with quarter cycle precision, exactly the way the 6309 expects. Wait states can come from two places: per device requests from the I/O decoder, and a global slowdown value from the local speed register. We simply take the maximum of the two. Whichever one asks for more time wins. No debate, no mercy. On top of that, there are several external wait inputs. If any of those assert, MRDY goes low immediately and stays there until the device releases it. Perfect for peripherals that need more than 3 wait states or can self-throttle. Because everything runs from the oscillator, known here as CLK4X, we synchronize E internally using a 2 flip-flop chain and detect its rising edge. That gives us a clean marker for the start of each instruction cycle. Each wait state equals 4 quarter cycles, so we preload a 4-bit counter accordingly. 1 wait state becomes 4 ticks, 2 becomes 8, 3 becomes 12. When run asserts, 1 counter counts down. When it hits 0, run drops automatically. No latches, no stuck MRDY, no late night "why is the bus frozen" moments. MRDY itself is asserted whenever either the counter is active or an external wait is present. Deterministic, gloriously boring, I mean simple. And finally, we have Shadow Plus, the PLD that refuses to specialize. This one handles 3 very practical jobs. First, it splits the CPU's read-write line into clean read and write strobes by gating with E. Some peripherals really want separate signals, and this keeps everyone civilized. Second, it manages shadow ROM behavior. On reset, ROM is enabled so the system can boot and copy itself over to RAM. All the while, RAM output enable is disabled. Once the ROM disable call occurs, a flip-flop switches roles. ROM disengages and RAM becomes fully readable and writable. One clean transition, no timing gymnastics. Yeah, it's basically an RS flip-flop with trust issues. And third, because debugging without LEDs is just guessing, a cute feature drives an RGB LED that shows the current real-time CPU speed. Red for full speed, yellow for half speed, green for quarter speed, and cyan for really, really slow. Not strictly required, but very useful, and extremely satisfying to watch. There are a few unused pins here too, reserved for future glue logic. You know, feature creep, or whatever idea shows up at 5 in the morning. And that's the PLD squad. 4 chips doing the work of a small pile of TTL logic without the wiring nightmare. Memory decode? Check. I/O decode? Check. Wait state control? Absolutely. Shadow ROM and speed indication? Oh yes. With these in place, the system finally has a brainstem, just enough discipline not to explode when we power it on. Shall we build? Quick confession before we begin. There was a small technical issue. I rearranged the components on the breadboard to save space, which is engineer speak for this was getting out of hand. Then I proceeded to add a few more components, only to realize afterwards I wasn't recording. Fantastic. Absolutely nailed it. That said, nothing critical was lost, and there's no point in reshooting just for the sake of historical accuracy. So let's pick up from there, and I'll walk you through what changed. On the first slice, we have the reset circuit, the CPU, the bidirectional data buffer with its damping resistor pack, and I replaced the old octal control line buffer with a 74HCT125, which is a quad buffer with individual output enables. On the second slice, we have the 2 address bus buffers, each with their own damping resistor packs. So, what's new? Still on the second slice, I added a green power LED because we like visual reassurance, a 4 MHz oscillator, and an ATF750C whose entire job is to stretch the clock using wait states. We'll call this one Wait State Gen because naming things makes them feel under control. On the third slice, you'll spot an RGB speed indicator LED. Next is an ATF22V10 that chops the address space into memory regions. That's the main decode. In the center, we've got yet another ATF750C responsible for generating device chip selects and requesting the appropriate wait states. And that's I/O decode. Finally, the last PLD is another ATF22V10 handling shadow ROM control, splitting the read-write line into clean read and write signals, and displaying the CPU speed in real time. This one is Shadow Plus, because miscellaneous but important doesn't fit on a label. At this point, ground and VCC are wired, decoupling capacitors are in place, and a few resistors are installed on the wait state generator PLD. Time to wire the new logic. The oscillator output goes to pin 1 of wait state gen, buffered E goes to pin 2, buffered read-write goes to pin 3, reset from the CPU goes to pin 4. The oscillator also feeds to pin 38 of the CPU, which is its clock input, because the CPU does enjoy knowing what time it is. For Shadow Plus, E connects to pin 2, read-write to pin 2, and reset to pin 4. Data lines D0 and D1 connect to pins 14 and 15 to wait state gen. The MRDY line is supposed to go to pin 23 of wait state gen, and yes, I initially connected it to MRDY code by mistake. That'll be corrected in the end of this segment. Speed bits S0 and S1 go from wait state gen pins 16 and 17 to Shadow Plus pins 11 and 13. Then continue onward from Shadow Plus to I/O decode pin 13 and 14. Speed select comes from MRDY code pin 19 and goes to pin 10 of wait state gen. ROM disable from ROM decode pin 20 goes to pin 1 from Shadow Plus. Memory request from MRDY code pin 21 goes to pin 5 of Shadow Plus. For the wait state bus, WS0 and WS1 from I/O decode pins 15 and 16. Then to wait state gen pins 11 and 13. I/O decode also gets the oscillator output to pin 1, read-write to pin 3, and I/O request to memdecode pin 2. Memdecode itself gets the E-clock on pin 1. The RGB LED is wired the sensible way. Blue to blue, green to green, red to red. Most importantly, no color theory crimes were committed. I do have a signed affidavit for that. And address lines A2 through A15, which are pins 2 to 16. I/O decode gets the lower address lines, meaning A0 through A7 on pins 4 to 11. And finally, remember the misconnected MRDY line? We fixed that and connected to wait state gen pin 23 where it belongs. And that's it. All that's left is to test the PLD logic. To do that safely, the bus request line is held low so we can simulate proper bus conditions without the CPU going rogue. I wanted to use the Arduino Mega to simulate all the conditions, but this episode is getting long as it is, so I'll do a quick manual montage of the testing process. Starting from the left, we've got the memory decode PLD. I added a small LED bar graph to make debugging less, theoretical. The three main regions behaved exactly as expected: constant block, I/O request, memory request. So far, so good. I then tested the 4 built-in I/O functions: ROM disable, speed select, IRQ, and FIRQ. And I immediately found a problem. ROM disable wasn't inverted. That's on me. I fixed it, recompiled, reprogrammed, and now it behaves properly. Up next, the I/O decode PLD. I walked through all 7 chip selects, or really 5 since the RTC eats 3 addresses like it owns the place. And yes, there was an addressing issue with the RTC chip select. That got corrected. Then came the wait state logic. Remember the lookup table I used to generate wait states? Yeah, well, that didn't pan out. So I rewrote it and actually simplified the entire thing in the process. Cleaner logic, fewer surprises, same results. Alright, 2 PLDs left. The easiest one by far was Shadow Plus. Separating the read and write signals was trivial to test. Clean pulses, correct outcome. But the Shadow ROM logic had a small flaw. ROM chip select and RAM output enable should not be inverted at the outputs. Easy fix. Change the polarity, recompile, done. LED testing will wait until the last PLD, which brings us to the final boss, the wait state generator. Testing wait states is actually pretty straightforward if you have an oscilloscope. You can clearly see the MRDY stretching the cycle in quarter cycle steps. The fun part is the software-controlled speed register. Watching the RGB LED change color as the speed changes is both useful and deeply satisfying. There's a limit though. MRDY can only be asserted for so long before the clock effectively stops. And with that, all PLDs are behaving. All in all, it looks good, which in electronic terms means time will tell. This project is going to have its ups and downs. I mean, how could it not, as it's a fairly large endeavor. In the next episode, we're diving into memory, ROM and RAM. And if the retro gods smile upon us, maybe our first lines of code. Don't forget to like, subscribe, and gently tickle that notification bell. Comments are always appreciated. Retro gods, give me the strength and the wisdom to survive one more datasheet without losing my last functional brain cell. See you in the next episode of 6309 Unleashed, upgraded, revised, and hopefully smoking only in the metaphorical sense. Thank you for your patience. Long story. to the ongoing, yeah, on a much brighter no. We're summoning good old 80s magie. Not in French, in English, magic. Because it was confident, but because I was. The combinatorial. And start acting like, and start. Yeah, that was right. I didn't make a mistake. I've been shaping what the 6309 needs. Needs. A bit more pronunciation, please. I've been shaping. PLDs handle address decoding. Jeez. Can you decode a goat? This is one reason the episode took me. Not all PLD outputs are created. How do I read cheated with created? Congratulations, you have a healthy compiler for you never. Just accidentally. Wow, is that really how we pronounce things now? More like Windows 98 server crashed, screensaver. Provides. The PLD code may evolve as we go. No, it's already evolved. The PLD code may evolve. Why do I put a D? Quick pause before we dive. I think I'm gonna change myself to AI. Oh, that's why. Gotta change that. I got glasses. I didn't have glasses. And if hand soldering has started for projects like this, where revisions happen and tolerances. On the first slice, we have the reset. On the second slice. See you in the next episode of 6309 Unleashed. Upgraded.